At 11:32 a.m. on October 30, 1961, humanity witnessed the detonation of the most powerful weapon in its history, conducted over an archipelago in the north of what was then the Soviet Union, at an altitude of 10,500 meters. This event would forever mark the history of military technology. But how did we get to this point? Let's dive into the journey that led us here. Since the late 19th century, scientists have known about the possibility of extracting energy through the separation of atomic nuclei, a process known as nuclear fission. Picture a uranium atom, relatively stable on its own. Left untouched, it wouldn't make much of a difference in the grand scheme of things. However, when a neutron is added to uranium, it becomes unstable. In its quest for stability, the uranium splits into two lighter elements, barium and krypton. Here's the intriguing part: if we add up the masses of barium and krypton, the total is slightly less than the original mass of the uranium. So, where did that lost mass go? Recalling high school lessons, according to Lavoisier's principle, in the universe, nothing is lost, nothing is created, everything is transformed. This lost mass was actually converted into energy. The energy released from the fission of a single uranium atom might seem insignificant to our daily lives. Yet, when you consider that a gram of uranium contains about 2.56 billion atoms, the narrative shifts dramatically. The complete fission of a gram of uranium releases enough energy to power 45 homes for an entire month. Impressive, isn't it? Rewinding to just a few months before the start of World War II, a German scientist named Otto Hahn achieved the first nuclear fission in history at his laboratory in Berlin. This moment officially ushered us into the nuclear era. But don't be misled by the term nuclear. Despite its potential to provide an extremely efficient energy source, one that could benefit countries with high energy demands in an economical and efficient manner, the term also carries a host of worrisome implications. The discovery of nuclear fission quickly spread around the globe, heralding a new era but also ushering in new challenges and concerns about how this formidable energy would be utilized. Rewinding history a bit, just a few months before the onset of World War II, a German scientist made history by achieving nuclear fission for the first time in his laboratory in Berlin. This moment officially marked the beginning of the nuclear era. However, despite the promising potential of nuclear energy as an extremely efficient source, its introduction was not without controversy. Nuclear energy promised a world powered by an incredibly effective source, where countries with high energy demands could see their issues resolved in an economical and efficient manner. The news of the successful achievement of nuclear fission spread quickly across the globe, heralding a new era but also introducing a series of challenges and concerns regarding its use and implications. But the euphoria was short-lived, as in 1939 Germany invaded Poland, plunging the world into war. The context had changed dramatically, and wars have a direct impact on scientific research and production. What was once seen as the promise of an extremely efficient energy source now paved the way for the potential of devastating weapons. Germany was leading this arms race, therefore, in 1939, a letter written by the Hungarian physicist Leo Szilard, and co-signed by none other than Albert Einstein, warned American President Franklin Roosevelt that Germany might be close to building atomic bombs. The suggestion was that it might be wise for the American government to start its own nuclear program. Spoiler alert, Germany didn't manage to develop the bomb, but shortly thereafter, in 1942, the Manhattan Project was initiated in the United States with the goal of developing atomic bombs. Just 3 years later, in 1945, the first nuclear bomb in history, a product of the Manhattan Project, was tested. And only 21 days after this historic test, the city of Hiroshima, Japan, was bombed. Shortly thereafter, just 3 days later, it was Nagasaki's turn. And just 3 days after the bombing of Nagasaki, Japan officially surrendered, thus ending the 6 years of World War II. The end of World War II, marked by the use of 2 weapons of mass destruction unprecedented in human history, did not mean the end of global conflicts. Particularly dissatisfied was the then Union of Soviet Socialist Republics, USSR. Just 2 years after the end of World War II, the world entered a new phase of tensions, the Cold War. This period was marked by the rivalry between the United States and the Soviet Union and represented the moment when humanity was closest to the end of civilization. During the Cold War, atomic artifacts were tested incessantly, mainly serving as a demonstration of power. In 1962 alone, 178 nuclear tests were conducted, 96 by the United States and 79 by the Soviet Union. Adding up all the tests carried out throughout history to date, more than 2,000 nuclear tests have been conducted. If you think the nuclear bombs like those dropped on Hiroshima and Nagasaki were the most potent ever created, then you've underestimated human capability. The bombs dropped on Hiroshima and Nagasaki were nuclear fission bombs, those based on the process I explained at the beginning of this video. However, there is an even more terrifying category of bombs, thermonuclear bombs. You might have heard about the hydrogen bomb or H-bomb, both terms referring to thermonuclear bombs. These bombs operate on the principle of nuclear fusion, a process where 2 light atoms, like hydrogen, merge to form a new atom with a mass less than the sum of the original masses. The difference in mass is converted into a significant amount of energy. The challenge of nuclear fusion lies in the need for extremely high temperatures to occur, such as the 15 million degrees Celsius found in the core of the Sun. And where could we find such temperatures on Earth? Interestingly, the explosion of a nuclear fission bomb can reach them. In simplified terms, a nuclear fusion bomb operates in 2 stages. The first is a fission bomb, similar to those used in Hiroshima and Nagasaki, which detonates and generates extremely high temperatures, on the order of 100 million degrees Celsius, more than 6 times the temperature at the core of the Sun. The second stage contains hydrogen, which serves as fuel for the fusion. This incredibly high temperature initiates the fusion process, which happens in a fraction of a second. The result is a hydrogen bomb, an extraordinarily powerful weapon that requires a nuclear explosion to activate. And here we circle back to the beginning of the video, flying at 10,500 meters altitude in a bomber over an archipelago to the north of what was then the Soviet Union, where the most powerful weapon in human history was tested. The energy of the Tsar Bomba was calculated to be 1,570 times the energy of the bombs that exploded over Hiroshima and Nagasaki combined. The bomber carrying it had to be painted with reflective paint to prevent overheating due to the explosion, and even so, the crew was given only a 50% chance of surviving the test. People 270 kilometers away reported feeling the heat of the explosion on their skin, and over 900 kilometers away, windows were shattered. But fortunately, we've moved past that era. Not everything in nuclear technology is about destruction. The energy used in those weapons can very well be harnessed by a responsible and mindful civilization, and that could be a ray of hope for the future. Mastering nuclear fusion might be the final step needed for us to become a civilization with access to clean, cheap, and efficient energy.